Hello everyone, this is Mr. Appel, and I'm going to walk you through this problem, which is a preview of what you're going to see in using linear programming to solve problems. So what we have are three different inequalities. Our first step is going to be to graph each of them. We're going to do this a little differently though, because these start to get messy when you have more than two inequalities. So when we do our shading, we're actually, instead of shading the solution, we're going to shade everything but the solution. And I'll show you what that looks like and why we do it in just a sec. So for starters, I'm going to start with the first inequality, x plus y greater than or equal to 2. I'm going to do that one using intercepts. If I put in 0 for x, then y is 2, so the y-intercept is 2. If I put in 0 for y, then x is 2, so the x-intercept is 2. So that's a pretty quick, easy way to graph to do that. And then I'm going to go ahead and draw the line. It's or equal, so it's going to be a solid line. Wow, that's a terrible line, but I'm actually going to fix that a little bit. And I'm going to show you why it's important to make that line a little better. I don't actually have a ruler on this tool, so you can hopefully do them better. I'm going to actually plot some other points that are on that line so that I can see them more clearly. And now I'm going to go ahead and draw my line as best as I can. Okay. And now for shading, I'm going to do my test point, which is 0, 0. And if I put 0 in for x and y, I get 0 greater than or equal to 2, which is false. So the solution for this region is not where 0, 0 is. It's not on this side. The solution is over here. So what I'm going to do is shade the opposite. And again, I'm going to explain why this makes sense, but I'm going to shade over here. And so I'm going to shade this side. So I'm shading the opposite for these problems. Okay, now I want to go ahead and graph the next one, the 4y less than or equal to x plus 8. So I'm going to do this one by putting it in slope-intercept form. So I'm going to divide everything by 4. So that ends up being y less than or equal to 1/4 x plus 2. It's useful to know how to do both options, slope-intercept and using intercepts, because it's good to be able to do both. So the y-intercept is 2, which is right there. The slope is 1/4. So I'm going to go up 1 and over 4. 1, 2, 3, 4. So that puts me over here, and then up 1 over 4 over here. And I'm going to go the other way and go down 1 left 4 to find some more points. It's an or equal, so solid line. And I draw my arrows. Again, with the shading, if I plug in 0, 0, I get 0 less than or equal to 2. That one is true. So the solution to this one is down here below the line. So I'm going to shade the opposite and shade above the line. Okay. Move on to the next one. 2y greater than or equal to 3x minus 6. I'm going to go ahead and do this one in slope-intercept form as well. So I'm going to divide everything by 2. So we get y greater than or equal to 3/2 x minus 3. So our y-intercept is -3. Our slope is 3 over 2. So I'm going to go up 3 over 2, up 3 over 2, up 3 over 2. I'm going to go back to the beginning and go down 3 and left 2 just to get an extra point. I'm going to go ahead and draw that line. Again, the test point 0, 0. If I plug in 0 for x and y, I get 0 greater than or equal to -3. That's true. 0 is bigger than -3. So again, the solution to that inequality is above the line. So I'm going to shade the opposite and shade below the line. So now if you look, by shading the opposite, what I can see, and I'm going to kind of zoom in a little bit here, is the solution set is this area in here, right? Because this is the actual overlap of all the solutions. And it becomes easier to see this little region here. This region is what we call the feasible region, meaning that's where all the solutions to this system of inequalities lies. Later, we're going to put this in the context of solving an actual problem, so that idea will make more sense. But again, the idea is that we've now identified that feasible region. What we're now going to be interested in is the vertices of that region. So first, I'm just going to kind of highlight that feasible region, right? That's our feasible region right there. And the critical points on this graph are going to be the corners, the vertices of that feasible region. So that shape is a triangle, so there's going to be 3 of them. One of them right here, one of them right here, one of them right here. Now, you may or may not have noticed that when I plotted some of those points, I can actually see where those coordinates intersect. So because I graphed this carefully, and if you use a ruler, you'll really be able to see, in many cases, you can determine those intersection points without having to solve algebraically. So for example, I see this point right here. They both hit the point 0, 2. So that's going to be one of my vertices is going to be 0, 2. Another vertex is going to be over here. You can see they both crossed there. That was at 4, 3. So 4, 3 is another vertex. And then the third one is going to be over here at 2, 0. So my third vertex is 2, 0. So in this case, we were able to determine all 3 vertices just from looking at the graph. But you can imagine there might be some situations where they may intersect in not so friendly places. And in those situations, we will have to go off to the side and solve algebraically. We'll have to solve that system of equations to find out where they intersect. Okay, our next step is to plug those vertices, plug each of those x-y pairs into what we call our objective function. And in this problem, I've just given you the objective function. It's right here. That's this function right here. In problems that we'll be solving, that objective function may have something to do with like a company's profit. So we might be trying to see which of these is going to yield the most profit. Or if we're trying to keep costs down, we might be interested in which one's going to keep the costs the lowest. So what we'll do once we've found those vertices is we'll plug each of those into our objective function and see which one is highest or which one is lowest. So if I want to plug in f of xy, and you'll notice this is kind of a new thing with function notation. So this is a function with 2 variables, and so this is how you show that in function notation. So this is f of x and y. So that means we're going to plug the first value in for x and the second value in for y. So the y value is 0, so I plug in 0 for y, 2 for x, and I evaluate that, and I get 2. F of 4 comma 3, that's x equals 4, y equals 3, so that's 3 times 3 plus 4, which is 13. And then f of 2, 0, which is 3 times the y, which is 0, plus the 2, which is 2. I definitely did one of those wrong. Let's see. I did the first one wrong. Let's go back. Hopefully you caught that. See, I do make mistakes once in a while. So it's 3 times the y value, which was 2, plus 0, which was the x, so that one is 6. So what we see is the 0.43 gave us the maximum value out of those. So 13 would be our max. And the 0.20 gave us our minimum value, so 2 would be our minimum. So depending on the problem, we'll kind of determine which one we're interested in finding. Again, out of context, this may seem a little strange, but once we kind of put it all together, it will start to make sense. So I hope that was helpful. Thanks.